Okay, this is the 9.2 instructional video from F30-1 where we start to talk about analyzing rational functions, and it's approached a little bit differently than 9.1 where we looked at transforming rationals and using that transformation language. 9.2 is really specific to rational functions, and what we're going to talk about is non-permissible values, asymptotes, and then something else called a point of discontinuity, which is going to be something really important that we talk about. Horizontal asymptotes will play a part here in as well. We are going to limit how much we talk about that. You really need calculus to get into it in any great detail. So when we talk about analyzing rational functions in 9.2, what we're really talking about in this case is some kind of a rational that can't just be transformed from y equals 1 over x. Now, I'm going to write this. It's going to seem weird initially, but the way I'm going to write that is I'm going to put a bunch of factors in here. So just x minus a, x minus b, and then I'm actually going to put x minus b in here again so we can talk about it, and then I'll just put x minus c in there. So think of this as the factored form of some, probably initially complex rational function. Now, certainly, we're going to summarize this at the review as well, but any factors, and I'll put that up here, any factors only in the numerator, try to spell that right, they correspond, and I'll give you an example of this on Desmos in a second here. So they correspond with x-intercepts, because if that particular factor is 0, the entire fraction is 0. Any factors that are in both the numerator / denominator, they are going to correspond, and I'll just abbreviate that, with what we call points of discontinuities. And that's really the new one, or the biggest new one. I'll make sure I spell this right. Discontinuity. That's the biggest kind of new concept in 9.2. And sometimes points of discontinuities are called a gap in the graph or a hole in the graph. And it's really the idea that only one value of x doesn't work, but everything near it is fine. And that's really similar to the vertical asymptotes, don't get me wrong. But what really makes points of discontinuities different is that they're in both the numerator and the denominator. I'm going to kind of color code this in a second so we can talk about which factors will be which. And then last but not least, there are the factors only, again, in the denominator. So that really covers all the possibilities, right? They're either in both one or the other. So factors only in the denominator correspond, oops, missed my R there, with our vertical asymptotes. Vertical asymptotes. All right, now what that allows us to do is in this particular graph, because x minus a is a factor that's only in the numerator, we could say that our x-intercept would be at what makes the factor 0, which is a in this case, comma 0. The entire, fraction would be 0. X minus b, on the other hand, is in both the numerator and the denominator. And we're going to talk more about this as we go, but that means that point of discontinuity is at x equals b. And then we'll talk a little more that we can actually find the actual point that it's at. So an x, and I'll just put maybe b, comma, question mark. We'll talk about how to find that question mark later in the notes. And then the last factor would be this x minus c, which is only in the denominator. So we would have a vertical asymptote at x equals c. Now that can be, that's the general concept that we're going to talk about today. Looking at that and just looking at that is difficult. And I think it's better to have that kind of graphical approach to this as well. So what I've done is I've made up just kind of a weird is maybe not the right word. I've made up a rational function and I've graphed it on Desmos. So nothing really all that crazy happening. Pretty clear there's a vertical asymptote right here. And that's probably all you can tell from this particular graph. But where this came from was this rational function. So there's a coefficient in there. We'll talk about that. That's just a vertical stretch. But then I have a factor that's only in the numerator. So that's x minus 1. A factor that's in the numerator and the denominator. That's the x minus 4. And then a factor that's only in the denominator. That's the x plus 3. Well, let's do the easy one first. Because x minus 1 is only in the numerator, that means that this point right here, 1 comma 0, what makes that factor 0 is the x-intercept of this curve. Really importantly, that is the only x-intercept. That's the only value of x that makes that fraction equal to 0. All right, the next easiest one, we're going to save the point of discontinuity for last, is the factor that's only in the denominator. Now, I'm going to make Desmos graph this. If we look at the line x equals, oops, negative 3, we are going to see, and I'll just make that a different color so it's a little bit easier to see, that that blue line is the vertical asymptote at the function. And I want to just look at what's happening with the function itself, which is this table of values. And what I've done here is I've put in numbers that are getting closer and closer to -3. And as the value of x approaches -3, the value of the function, or the absolute value of the function, becomes very, very large. And we see that the closer this x value is to 3, there's that -3.5 right there. The closer I get to -3, the larger the absolute value of this function is, and it has that asymptotic behavior where it's veering kind of up to positive infinity on one side and down to negative infinity on the other side. Then the last one, and that's what I'm showing with this value, is what we call a point of discontinuity. Now this point of discontinuity is at x equals 4. So I'm going to try to find it on Desmos. I might have to go a little closer. If we looked at 4 itself, all right, we'll get there. Got to go a little bit closer yet. We'll get there. 4, comma, undefined. Desmos gives up. Now, if you try to do this on the calculator, it'll just leave the y blank because there is no y there. What's really important is that x can't be 4, because if x is 4, we're dividing by 0. But it's a unique case where we're actually dividing 0 by 0. Now, this is an entire chapter in calculus, so we can't get into it in too much detail. But the key difference between these two table of values is that here the function is getting really, really big, and it's just going off to positive infinity. But if we look at this table of values, as my function gets closer and closer to an x value of 4, the value of the function gets closer and closer to an actual number. Now, the real question that we're going to deal with is, how do we find what that number is? And it's actually easier than you might think, which is kind of nice. I hope we all agree that based on this table of values, it sure looks like it's about 3, right? In between 2.99 and 3.005. The way that we can actually do this algebraic, I'm going to write on Desmos itself, is we could take that function. So if we took f of x and did some simplification, so I'm going to write it all out here again. But if I take this f of x and I try to find its simplest form, logically, those two factors would cancel. So now I have that f of x is equal to 7 times x minus 1 over x plus 3. Now what's really important is that these are no longer the same equations. Because if I just gave you this bottom form that I'm putting a box around, there is no problem with putting positive 4 into that equation. What's tricky about this, and I probably should have called it g of x or something, is that although they look like the same equation, they're actually not, because this bottom function, I can figure out what f of 4 is. Right, putting 4 into that bottom function doesn't make me divide by 0. And when I do that, what I get is 7 times 4 minus 1 over 4 plus 3, which is 7 times 3 over 7. The 7s would cancel, and I would get 3. Now, what that means is that on the red graph, the original graph, this guy in the actual table description, 4 comma 3 doesn't exist. That's a hole in the graph. It's a point of discontinuity. It's not there. But what this in asterisks allowed me to do is it allowed me to look at a function that looks the same everywhere except for 4, because it exists as 4, and basically approximate where that point of discontinuity will occur. And really what I can do now is I can say that this open dot, which would be right there, that it does exist. The open dot exists on the function. That point of discontinuity is going to be at 4 comma 3. And this is definitely something that's a little bit tricky about chapter 9. It is going to involve a lot of factoring rationals and then basically checking which factors are only in the numerator, only in the denominator, or in both, and then following that guide that I wrote up here. Now, this is also in your textbook, but I think it is useful to write it down because that does help us to remember. The only thing that my form didn't miss, and this is just on me I kind of forgot, I'm just going to make it a capital A, is that there could be some kind of a vertical stretch there, and that actually wouldn't change any of this information, which is kind of nice. And that's because that number is a whole number. It doesn't have a variable in it. So the value of x doesn't change what that capital A is. All right, that's the instructional video. Definitely a bit of a trickier lesson. We're going to try to go through these examples in really, really good detail to help you understand it.